Hi Kidlets, this is your third notes video for this section on stars, and we will be talking about stellar properties and how to measure stars. So the first property that we are going to look at is how do we know how far away these things are? We've already talked about how our closest star is approximately 4 light years away in the Alpha Centauri complex, but how can we say with confidence how far away distant stars are when they're 30, 40, 60,000 or even million light years away? And we do that by measuring something called parallax, and we looked at this last semester as well. So we can't use this for things that are really far away. We have to use other measures like indicator stars, like Cepheid variables, or type 1 supernova, where we know they have a constant brightness, so we can use those to measure distance. But for things that are close by within our galaxy and within our solar neighborhood, we can use parallax. And this allows us to study in depth close by stars that we couldn't do if they were further away. And just as a recap, parallax is looking at the movement of that star against the motion of the background stars from two different locations. The furthest apart Earth can be, as we've already looked at, is on either side of the sun, so 6 months apart. So we would say, January, June, February, July, and looking at where that star appears against the sea of background stars and then measuring that angle. So here again, we can see the star seen against the background stars in January and the star seen in July. And by measuring that angle of movement, we can get an approximate distance. So the way we actually measure parallax is with this pretty simplified equation, which is just 1 over the parallax angle. And that gives us a distance in parsecs, which we then convert to light years. So parsecs and then megaparsecs is a way of breaking down the sky and the universe into smaller and smaller numbers, so something that is actually measurable and calculable. So for example, if we were to look at Sirius that had a parallax angle of 0.379, we would do 1 divided by 0.379, and that would give us our answer in parsecs, which we would then multiply by our distance in light years to get us an answer. So we know that all of these parallax angles are going to be very, very small. So we can see that the further we get away, the smaller that angle is going to be, which is why even with very fine instrumentation, this really isn't possible for stars of a great distance. So I would expect that you would be able to calculate each of these problems. You may be given them in class, so definitely make sure you're familiar with that very simple equation and what the conversion factor is from parsecs to light years. PC is the symbol for parsecs. Megaparsecs would be MPC, big M. Stellar brightness and luminosity is another property of stars that we're going to be looking at. And last semester, again, we took a look at magnitudes and how those are a measure of brightness. And then the brightness is the result of how much energy that star has. But there's two different ways we can measure brightness, because obviously from Earth's perspective, that brightness is distance dependent. So if we take a look at this little image down here, we can see that from this observer's perspective, the kid who is closer with the bike light appears the same brightness as the truck and the headlights that is further away. So we know intrinsically that this is going to be brighter, but because it's a greater distance, it appears the same brightness. So that's why brightness is density dependent. So we can use magnitude to then say how bright the star actually is if it's not distance dependent. So we have two different things that influence stellar luminosity. We could say that the luminosity is that overall measured brightness of a star, the overall energy of a star. So how big the star is. So the radius is a quadratic relationship. So we know that the luminosity is equivalent to the radius squared. And we could use that in the opposite as well. If we knew the luminosity, we could determine what the size is. So how big the star is and how hot the star is. So the luminosity here is equivalent to the temperature to the 4th power. And these are both really important functions when we look at stellar evolution, when we look at what our close-by stars are, when we search for habitable planets, because it's a very particular size and temperature star that could produce planets that could be in the Goldilocks zone to possibly support life. So how big a star is, how hot a star is, influences the overall luminosity. So here looking again at brightness and distance, we have star A, we have star B, and Earth. So even though A is further away, they could appear the same brightness. So we call that apparent brightness. But what we really want to use is the absolute brightness, or the absolute magnitude. So apparent magnitude would be distance dependent. Absolute magnitude is not. So if we were to place all stars at the same distance, and that arbitrary distance is 10 parsecs, which remember that 1 parsec is 3.26 light years, so 10 parsecs would be about 30 light years away. So if we put them all at the same distance, what their brightness would be, and that's absolute magnitude, and that's a much greater indicator of how bright a star is going to be. So absolute magnitude versus apparent magnitude. And if we look at the magnitude scale again, remember that 0 is anything above 0 is going to be very faint. Anything below 0 is going to be brighter. So looking at just some reference points, the apparent magnitude of the sun is -26, but we know that the sun is not a very bright star, so that is distance dependent. If the sun were actually put at a distance of 10 parsecs, it would be about a magnitude 4. It would almost be at the naked eye limit, which is 6. So we can see Venus at its brightest. Venus is very bright right now. And we can see how far Hubble can view, which is a magnitude 30, and James Webb will be able to view at a magnitude 90. So this is a logarithmic scale in which every difference in about every 5 magnitudes is 100 times greater brightness. So we've already looked at this image of the star field before. I would expect that you would be able to pick out what the brightest stars are, what the faintest stars are, and we should be able to see that we've got what looks like Rigel is a pretty low number, but we got Betelgeuse that is above a 0, so it wouldn't be very bright. We have nothing below a 0, but this is the lowest number. So Rigel would appear as our brightest star, and then our faintest star would be the highest number, which looks like Hatsia. So obviously, the bigger the star, the brighter the star, and that relationship is quadratic. If we square the radius of a star, we can get what the luminosity will be. So it's not a linear relationship. It increases as a square function. So another problem that I would expect you guys to be able to solve would be looking at a sample star. In this case, I give you Polaris. It's about the same spectral type, which would indicate the same surface temperature as our sun, but it's a 10,000 times brighter. So I would expect you guys to be able to figure out how much bigger Polaris is than our sun. So the hint I gave you is that you'd be solving for the right side of the equation. So you'd be taking the square root of 10,000, which would give you 100 times greater brightness. So spectral class has to do with how hot a star is. Remember, we said luminosity is both dependent on radius and temperature, and spectral class is determined by the temperature. Spectral class is by sequencing the star's color and attributing that to how hot or cooler the star is. So we know that all stars have very similar compositions. They're all beginning with predominant hydrogen and converting those lighter elements into heavier and heavier elements, but they all have very different temperatures. So our spectral classes are broken down into these letters, and we can, for our intents and purposes, omit LT. But this is the spectral class. So the way that you can remember that is this ridiculous acronym that goes, "Oh, be a fine girl, kiss me," or guy, whatever your preference is. And I would expect you guys to commit that to memory and to know which stars in that sequence are going to be associated with your very hot and bright stars. In this case, it is our type B and O stars, and our cooler red stars. And our sun is a class G star, so it is not very big, it is not very bright, and that would be right about, sorry, I can't change the color right now, right about there. So we know that the color of a star is indicative of its temperature, and I love the constellation Orion because it shows us so many different phases of stellar evolution. We have a nebula, which is where stars are born. We have Rigel, a blue giant. We have Betelgeuse, which is a red giant star. So Rigel is actually still on the main sequence, which we'll talk about more in the next session. But Betelgeuse is a sun-like star that is nearing the end of its life. Rigel, a massive star, so they were born different. And here we can see with some different filters, we can see a lot of cooler red stars, and if we can see a lot of red, that tells us that this is likely in the infrared because it would be scattering the bluer wavelengths. So looking at the breakdown of spectral class again, O, be a fine girl or guy, kiss me, and remember that we are omitting, for our purposes, we are omitting the L and the T, because really when it's below this temperature, it's not hot enough to complete fusion anyway. So these would be more like Jupiter-ish style stars that didn't really have the mass to attain the temperature to complete the solar or the stellar processes in order to become a star. So you can see that our type O stars are our very blue, violet, very hot stars, whereas like our sun, which is this guy right here, which is why we see it radiating in the yellow, about 5,500 degrees Kelvin. And remember, this is measured at the surface, which is the photosphere. We know that the corona, the outer layer of atmosphere, is hotter, and the core is hotter than that. But what we consider the surface, where that peak of black body radiation is, we would see in the yellow, which is an indication of this temperature. So here we can see again the spectrum of our very warm stars, our type O, type B, all the way out to our very cool stars, which would be a class M. So, and we can see the range of colors related to these. So stars that are born over on this side of the spectrum are born with a lot more mass, a lot more gases. But as we'll see, even though they're born with more, they go through it faster. So these stars tend to live very, very short lives, whereas these stars can be as old as the universe is. Our star, a class G, will live about 10 billion years. These stars can live under a billion. These stars can live 30 billion. The universe is only 14.5 billion years old. So we can have stars that can range the full gamut. And the early universe was populated with predominantly these, which then exploded in supernovas, which dispersed heavy elements into the universe, and including into you. You are essentially made of stardust from the earliest stars exploding. So that is it for this section of notes, guys. Have a fantastic day, and make sure you understand all of the different functions for those simple equations that I showed you, and come to class prepared to solve some practice problems.